So the previous speaker said that he woke up at 4. Okay, 3:30. I couldn't make it yesterday, and the flight was really early this morning. So if I turn off at some point of my talk, just wake me up. Okay, so my plan for these 3 lectures is to tell you about a series of classification problems which fits in a similar framework. And my plan is to first give 2 examples which look of a very different nature. Next talk would be like, well, let's see which is this common framework in which we can work out these 2 examples. And depending on how it works, then in the last talk, I will take about some, future directions, right? That's the point. Okay, so I have a co-author which says that classification problems can be very wild. Yeah, so I'm going to tell you about 2 wild classification problems. The first one is, well, classify. Is it visible? I think it's maybe too small. Too small? Oh, it's perfect. Okay. So classify CW complexes up to homotopy, for example. So up to homotopy, and the answer is no hope. Yeah. So the reason I'm going just to sketch, because I've never looked in detail at the reason, but the reason is it has to do with the problem of classifying finally presented groups. It's proven that you cannot classify all finally presented groups because of these word and subgroup problems. And you can realize any finally presented group as the fundamental group of a CW complex, and that's how the story goes, right? The second is given a finite group G and a field K. It could be classify all let me write KG modules up to isomorphism. And what do I mean by a KG module? So you can unpack this definition, and a KG module will be a K module with an action of the group G in which everything is compatible, right? And you can put these 2 compatibilities together by constructing this group algebra. The elements are just K-linear combinations of elements of the finite group G. And then you can multiply by using the multiplication in G and use the distributive law, and then you produce this KG algebra. And then when a KG module, what it does is just puts together the action of the group G, the structure of a K module, you put everything together, and then you can just talk about KG modules. I'm going to tell you later why this is also a wild problem, right? You can write finally generated if you want, and it's still a wild problem. It's not about being finally generated. Okay, so what I want to tell you is what can be done in these both situations, right? So the first one. So I'm going to talk about some work of which has been already mentioned in the previous lecture of Hopkins and Smith. And but for this, I need to introduce what's the stable homotopy category, what's a spectra. So I don't know if everybody is familiar with it, but I will do just a very brief introduction, right? So the idea is to change the homotopy theory, but the stable homotopy theory, and try to see what stable buys for us that makes the classification problem more accessible. So what's a spectrum? I can hear myself breathing. Is it? Can you hear? Okay. I'm getting more and more nervous when I hear myself breathing. Is it okay now? Okay, much more better, yeah. So what's a spectrum? E is a sequence of spaces index over the integers with what are called some structure maps. And these structure maps, they go from the suspension of En into En plus 1 for every N. So that's the definition of a spectrum. And what's the kind of the motivation? Well, it comes from, well, Freudenthal's theorem, which tells that you start with a space X and you look at some homotopy groups, and then that's a map from the sphere into X. You make the suspension of this map. You have something from the sphere K plus 1 dimensional to the suspension of X, and then you can iterate. And this theorem tells you that these abelian groups stabilize. So for some big N, which depends on the connectivity of the space, and I'm not going to describe it, but for some big N, this sequence stabilizes. That means that next one will be isomorphic to the previous one. Yeah? So you can take the limit with respect to the variable N, and you get what is the stable homotopy group of X. Right? So the stable homotopy group of X would be like this limit of yeah. And then you can look at the stable homotopy groups, and then you could ask whether there is a category, a context, in which these stable homotopy groups are really homotopy groups from the sphere into X. Right? And the other motivation for considering such objects comes from cohomology theories. Right? So there is this Brown representability theorem, which says that any generalized cohomology theory satisfying the corresponding axioms is represented by a sequence of spaces. So that means that if you have H star, some generalized cohomology theory, I think you need reduce and go to pointed. Let me see. Then there exists an N such that this corresponds to pointed homotopy classes from X into some En, right? And the suspension axiom, which says that the reduced homology of the suspension is just shifting the reduced homology of X, then is that what produces these structure maps. I mean, from the Brown representability, from this theorem applied to a cohomology theory, you obtain a spectrum, and the other way around, right? And if there is an adjunction that goes from En to loops to En plus 1, this is the adjunction of this map. When this is an equivalent, we are talking about omega spectrum, right? So, and then you can organize these objects in a category. and you want to describe what are the morphisms, and the morphisms will be just morphisms degree-wise, continuous maps degree-wise, which respect the structure maps. Right? So if you have, so you have a morphism, if you have a spectrum E and a morphism to a spectrum F, will be just a collection of fn's, and then such that when you take the suspension these diagrams commute. Yeah. And so the point of considering a spectrum is that you can consider the following factor. So we organize this in the category of a spectra. And so we are considering an endofunctor which takes a spectra E to the suspension spectra, which is just in degree n. This is just En plus 1, right? And this is sometimes it's called the shift functor or the suspension functor, and this gives you an endofunctor of the category, which is an equivalence. So there is also sigma the minus 1. So you can shift. And what else do you have? You have given a space X, you can smash a spectrum with a space. You just do it degree-wise. And moreover, you can smash a spectra with another spectra, but I'm not going to go into the details of this because that's a more delicate matter, right? So, but just believe me, yeah, that you can, and given E and F, there is also the smash of two spectra. And I'm going to use, at some point, I'm going to use this notation. Because what you want is you want to have a nice smash product of two spectra, which gives you more structure to the category. It's going to give you a monoidal structure on the category of a spectra. Yeah? So, examples, so I forgot to give you some example. Well, if X is a pointed topological space, you can just consider the suspension spectra of X, which in degree n has a point if n is negative, and you just write the suspension of n. If n is positive, you iterate the suspension construction, and well, if n equals 0 is the identity is X, you do nothing, right? And if X is just a space not pointed, then I will write this to denote which is the suspension spectrum of X when I add an extra base point, right, to make the construction. And another example, I mentioned cohomology theory, so another example that will appear at some point is that the Ellenberg Maclean spectra. So if R is a ring, is a commutative ring. Well, in most cases it will be just a field. You just look at the spectrum which you get from realizing the ordinary cohomology theory with coefficients in R. And what you get is, I'm going to use this notation, HR, to denote the spectrum, which is the HR is, HR is K Rn is n then 0 and sorry, 0 and then oh yeah, no, that's correct, yeah, and a point otherwise. And then there is this relation that you have a map from loops of K Rn plus 1 is equivalent to K Rn. So this is going to give you, in fact, an omega spectrum. Right? And so we have this category now. We have we can view spaces inside a spectral, taking the suspension spectrum. We have more objects. We have K theory. K theory also gives you a spectrum with BU and it's Z cross BU in even and odd places. And then the yeah, exactly. The question now is, we want to use this extra structure instead of looking at objects individually and trying to classify single objects up to some notions of equivalence, up to isomorphism, for example. What we will do is we will use this extra structure to try to classify certain type of subcategories inside the spectrum, right? And yeah, just a comment. There is a notion of homotopy. Just when you smash with the interval, you have the notions of homotopy, and then you can talk of homotopy. You can construct the homotopy theory of spectra, and you can talk of cofiber sequence. You can reproduce the homotopy theory with these objects. Right? Just replace X by the interval, and then you can make sense of homotopies. Right? And so now I have this is 3. I'm not sure I will be able to write some a lot on 3 because it's a bit high, but so let's give a definition. This is in the work of Hopkins and Smith. And it's the following, so a full subcategory C of spectra is said to be thick if it's close and the following and the weak equivalences. That means that if a spectra is in C, all other spectra which are weak equivalent to it must be in C. Cofiber sequences. So if you have a cofiber sequence and you have a map from E into F, and then you take the cone of F, yeah? Or then, and it makes sense because what I said, I can develop the homotopy theory. So cofiber sequence, that means that if 2 are in C, then the third must be in 3. So that means that 2 out of 3 in these cofiber sequences. Right? and retracts. So if you have a spectrum in C, any retract must be in C, right? And so the goal is, instead of classifying the objects and the isomorphism class, which comes within the category, the goal that Hopkins and Smith achieved is to classify all thick subcategories, right? And which information is giving you this classification? So it's telling you have two objects, you can see when you can build one object from the other or the other way around by using these constructions in the category, using cofiber sequences and using retracts, and using all this machinery that now this category of spectra has. So the question now is not to see when two objects are isomorphic. The goal now is to see when you can construct one object from the other using these techniques, right? Inside the homotopy theory of spectra. And so the answer, so let me see. So the answer is somehow a bit related to the previous talk, because these maps Bn appear because in this paper they use what is called Moravacay theory. So what they are going to do is, given these objects, they are going to detect the properties of these objects using a family of cohomology theories. So let me see. So the proof uses a family of homology theories of you have one for each prime and each natural number, except for n equals 0, and you have p a prime and n a natural number, n bigger than 0, then I'm going to tell you which are the coefficients of these theories, right? And you will see some familiar have bn minus 1, and the degree of bn is 2p to the n minus 2. And for n equals 0, k0 star is just hq star. I mean, it's rational cohomology. At level 0 is just rational cohomology. Yeah, so okay, so given, well, the first, we say that E spectra is p-local if the homotopy groups are going to be the stable homotopy groups. So that means that homotopy classes in this context from the sphere spectrum into X. So if are p-local, abelian groups. And there is a localization which takes your spectra to a p-local spectrum. Right? And then, so the theorem, the classification, let so yeah, the theorem goes in two parts. First, if you take, they show that if you have a thick subcategory of finite spectra, so now everything will be inside finite spectra. So you can define what's a CW spectra with the same notions that you use for spaces, and then you can talk about finite CW spectra. So these are the context in which we will be looking at these thick subcategories. We will thick subcategories inside finite spectra. Then is going to be of this form. Let me tell you for some n. Of p-local finite spectra will reduce to, and these categories, these thick subcategories, say X is in one of those categories if only if the Moravacay theory applied to X is 0 for all m less than n. So, and the other way around is to show that all these categories are thick. So there are two ways in this theorem to show that these categories are thick, and then the hard part is to show that any thick subcategory will be of this type. Right? So that means that these thick subcategories are determined when you p-localize you take your spectra, you p-localize, and then you just look at, you just check for which ends the Moravacay theory of X is 0. So you can make a picture of these subcategories. So you have at the level 0, you have rational cohomology, and then when you go up, you have for each prime you have a cohomology theory. So you have, so this would be, usually it's called 0, 1, and then here you will have 1, 2, 1, 3, 1, 5, and so on. And then for n equals 2, you have the same dots, but now it's 2, 2, 2, 3, 2, 5, etc. And then you have these columns that they are up here. So, and then at the bottom you have rational cohomology. Yeah. So that tells you that you take your space X. When you p-localize, it's like that you fix one of those primes, you fix one of those columns, and then your category is determined by the first value of n in which this m does not vanish. Right? And well, there is a theorem that says that if km is 0, then km minus 1 is 0, so there is no problem with that. Right? So that says that any thick subcategory of a spectra can be determined by a subset of this set here in the picture. Can be the empty, can be, or can be just a union of subsets of these columns, which means you fix a level in the column, and then you just have a prime and an n, and you have different primes and n's, and that determines all thick subcategories in the category of finite spectra. Right? So, yeah? Yeah, they include. Yeah, exactly. Higher up is smaller. Yes. Yeah. Yeah. So this is one situation in which introducing this stable structure using taking these sequences and this shift functor and doing homotopy theory in this context helps to give an answer to a classification problem. So now you know when you can decide whether one spectra builds another, or when they just you take a spectrum, you look at the smallest thick subcategory that it generates. So this one is determined by primes and natural numbers and nothing else, right? Okay, so now board 5. Okay. So now we go to question number 2, which is about representation theory. Now we have a finite group, a very different context from the previous one. Have G a finite group and K a field. And it's still there. So the question was whether we can classify all KG modules up to isomorphism. So let me give a name. This is going to be the category of KG modules. Objects are KG modules and morphisms are morphisms with respect to the structure, and then I will use small letters when I'm adding finally generated to the picture. Yeah? So this is the category of finally generated KG modules. Okay. And the problem is to classify all possible representations of G in this context. So the first problem, well, is that depending on the characteristic of the field, the situations are very different. So if P, which is the characteristic of the field from now on, does not divide the order of the group, then the situation is manageable. And the reason is that there is a theorem, Maschke, which is, I think it's from the 19th century, that says that by 1 year, that says that any representation is isomorphic to a direct sum of irreducible representations. So you reduce to classifying irreducible representations, and then there is a character theory that helps you with that. And you have function classes, and you can make tables classifying irreducible representations for the group. So every representation or every KG module of G is isomorphic to a direct sum of irreducible representations. I mean, the essential point is that in this context, every short exact sequence of KG modules splits. That's it. And the idea is that if P does not divide the characteristic ID order of the group, then you can average. You can just add all possible preimages, divide by the order of G, and you can construct sections. Right? But in general, but this is not true if P divides the order of the group. Right? In that case, that's not true if P divides the order of the group. And even this, if you take the group algebra and go to the trivial representation where the elements of G are trivial, multiply trivially here, and this is just the augmentation that every element of G goes to 1, so this is like adding all the coefficients of a linear combination of elements of G, does not split. Yeah. then, well, what can you do? Well, you can try, right? And then there are a result that tells you that you can even try to see if there is a finite number of irreducible representation. And one of the problems is that the word irreducible and indecomposable are not the same. I mean, Maschke's theorem is telling you that indecomposables are irreducibles, but here indecomposables and irreducibles are not the same. Okay, so if you have an invariant submodule, this is a submodule, but you cannot reduce it from the big one. You cannot split it. Yeah. So there is a result that says that G has only finitely many indecomposable representations. Now the goal, since they are not the same, is try to understand indecomposable representations. Representations, if only if the CeLO P subgroups of G are cyclic. And it's an if only if. That means that if the CeLO P subgroup is the maximal P subgroup of G, and P subgroup means that the order is a power of P. Right? And so this is an if only if statement, so that gives you lose hope when you see this statement. I mean, if the CeLO subgroups are not cyclic, then you will not have finally many indecomposable representations to start with. And only in a very few cases in which the CeLO is not cyclic, I think it's dihedral, semi-dihedral, and quaternionic. Only in those cases you have families, and you can classify indecomposable in families. But in general, you don't even have this situation, right? So that's why I distinguish. This is what's called ordinary representation theory. This is modular representation theory. And these are the good groups to play with. And then when the CeLO is quaternionic, semi-dihedral, or dihedral, it's what's called a tame situation, the tame representation theory. But apart from that, this was a wild representation theory. Okay? So the idea is to somehow use what we learned from a stable homotopy theory and try to construct a framework in which we can play a similar game. Right? And that goes down by several authors. And so what I'm going to mention is basically work of Jeremy Rickard and Benson, Carlson, Rickard. And we are going to construct the stable module category. And the idea is the following. You have Mn, which are in mod kg, two modules. We are going to define new morphisms. These are abelian categories, right? So you can look at let's write kg. And then here we quotient by a linear subspace, which is the following, where P kg Mn is the linear subspace of kg Mn of those morphisms from M to M which factor through a projective. Right? And so in fact, the category of KG modules is, in the category of KG modules, let me say some properties which, in this category, injectives and projectives are the same. And this category has enough projective and injectives. This is what sometimes is called a Frobenius category. So so saying that it factors through a projective, it's some sense it's just saying that it factors through the projective resolution of n, or the injective whole of M that can reduce to this situation. And so the point, and then the stable module category is the category in which the objects are KG modules, but the morphisms now are replaced by these new morphisms. Right? It has the same objects as mod KG, and the morphisms now are this underbar om. And why it's called stable? So what we had in the stable category was this end functor with this suspension, this shift. Okay, so we are going to construct a similar end functor within this category, and we do the following. So there is a shift or suspension. Sometimes it's called loops -1, or I will just call it suspension in analogy, but that goes from this stable module category. And how is it defined? So M goes to, and this is the cocker of the map that goes from M to its injective whole. Okay, and but look at the following. So if you have this suspension of M, this module is like the trivial module in this category, right? So that's the reason that mimics this suspension. And another, when we describe a thick subcategory, we use cofiber sequences, for example, right? Cofiber sequences here will be replaced by exact sequences. Okay, so, but let me tell you what is an exact sequence here. The exact sequences that go zero. Now I don't have enough space. Let me write this. Here, so it's if you have exact sequence, you can do the following. You take L, M, N, and here you have L. And then here you have the injective hull of L. And then here you have the suspension of L. Right? And what happens is that the injectives are also projective. I have a map here. And no, that's because it is injective, sorry. And then once you have this, you have a map here. That's how it goes. So if you have exact sequence, you can go to the suspension of L. You can follow the sequence inside the category, in the stable module category, right? And this mimics also what happens in the stable homotopy theory, that you have cofiber sequence that you can follow by the suspension, and then you have another cofiber sequence. Right? So let me see. So we can reproduce much of these constructions that we have in the stable homotopy theory. So you can make sense also to the notion of a thick subcategory, right? Weak equivalences are isomorphisms, and then you have cofiber sequences are exact sequences, and then you have, well, retracts. Retracts is just a section, right? So you can make sense of this definition, and you can considering looking at the thick subcategories in the stable module category, right? And that's what's in Rickard started developing of this theory inside the stable homotopy in the stable module category. And the goal is to classify, right? So the result, okay, I have to change Blackboard too. But there is something we need. Oops. I might need help. I was too optimistic when I pushed that. Okay, thanks. But what we are missing somehow is where we compare to. I mean, for the stable homotopy theory, we had these Moravacay theories, right? Which were these functions. We were able to construct a function from x to this set of n cross primes. And to each x, you could associate the type of this x, which will be a pair of numbers, right? We don't have this here yet. So we have the stable module category, but we want to associate something that allows you to classify, saying, well, any thick subcategory will correspond to some subsets of whatever, right? So we are missing this point. And let me just briefly tell you how to get there, and that involves a bit of group cohomology, right? But I will be just very brief. So if G is a finite group, you can look at group cohomology. What's group cohomology? So group cohomology you can look like being the X functors in the category of KG modules of K from K to K. And these are the derived functors of the OM functor. Right? So you can look at the derived functors of the OM functor in this category. So you take a projective resolution of K, you apply OM, and you get this cochain, and then you do kernels and co-kernels, and images, and then you get the cohomology, right? And this is X. You can think of X as the cohomology of some complex that you obtain from a projective resolution of K. But on the other side, which is really nice about group cohomology, is that each finite group has associated classifying a space, right? And this is a nice topological space, right? So, and you can compute singular cohomology, cellular cohomology, the cohomology that you like. So this is also the cohomology of BG. And the connection is that I didn't say what's BG. BG is KG1. That means that the homotopy groups of BG are G in degree 1 and 0 otherwise. Right? So it's a connected space, and then the fundamental group is G, and the rest are 0. Right? And so that's, and the way that connects is because if you take BG and you take the universal cover of BG that has a G action, and when you look at the cellular complex, you have an exact, since the universal cover is contractible in that case, so what you get is just a free resolution, in fact, of K with G modules, and that's the connection with X. Right? And then the good point is that the cohomology of G is finitely generated K algebra. That goes back to work of Golod, Evans, or Benkov. And there are several ways also to see quickly. One quick way of seeing this is that G has, if you take the regular representation of G acting on itself, that gives a free representation, and embeds, that gives you an embedding of G into a unitary group of matrices, which is permutation matrices. And then if you look at the fiber sequence BG BUN, the fiber is finite. And then the spectral sequence has, since it's finite, so a spectral sequence it's just just a row, just several rows, and then it's 0 up, and then this collapses. But the cohomology of the unitary groups, it's polynomial. We know it's finally generated, and then you use some commutative algebra saying that in this situation, since the cohomology of BUN is noetherian, in fact, and the cohomology of G is finite over the cohomology of UN, then you get. I mean, it's not. It's just an argument that can be explained. But that's important, because then when you know that this is a finally generated K algebra, graded commutative, that's you are in the wall of commutative algebra. Okay? So you can look at, for example, the spectrum of homogeneous prime ideals. That could be an important object that will appear. Right? And so what we are going to do is, you can just, the other point is that if you take M a KG module, turns out that if M is a finally generated KG module, then X KM KG, which is the cohomology of G with coefficients in M, right, is a cohomology of G module. And remember that we want to start with module M, and to this module M we want to hit something in another set, which is easier to identify, or something that then we can use to classify, like Moravacay theories were doing this job finite spectra. So we start with a KG module. I look at the cohomology of G with coefficients in M. Turns out that it has the structure of a module over the cohomology of G. Yeah? So what we are going to look is, you look at the annihilator as a cohomology of G module. I'm being very sketchy here, just to give you the idea of how we can associate something to M. So we look at the annihilator, so these elements of the cohomology of G that that when you multiply for any element of the cohomology of G with coefficients, it's 0. That's the annihilator. So this is an ideal, and this is an ideal in the cohomology of G. And then we consider the following set. We consider the primes, the prime ideals, let me just, which contain this annihilator. Let's call it this A. Okay, and cohomology of G is the spectrum of homogeneous prime ideals of the cohomology of G. Right? So we start with the module. We look at the cohomology with coefficients, and then we look at the annihilator. This is an ideal in the cohomology of G, and we take all prime ideals which contain this one. So this is something which sits inside the spectrum of homogeneous ideals. Right? And then this is what it's used to classify thick subcategories in the stable module category of G, right? And so Benson, Carlson, and Rickard, they establish a bijection between thick subcategories of, I write a small letters, means finally generated, of KG. There is a bijection with subsets of, let me write brush of the cohomology of G. This is the spectrum where we remove the maximal ideal of elements of maximal degree, I mean of positive degree. Close and specialization. Close and specialization means that if subsets, because that means that if I have a Q and Q is contained in P, then P is also in here. And this is true, but only if G is a finite P group. That's the case for the finite. But this was the starting point then to build other classification results. So the idea is that now you can decide whether two modules can be constructed from each other using all this structure that we have built in the stable module category by just checking that some subsets in the spectrum of prime ideals are contained in each other or they are equal. Right? Benson, Iyengar, Krause, then just establish the results for finite groups, but that's maybe it's yeah. So I will stop here. Just extended this result to the corresponding statement, because then there is, instead of brush, you have the full spec, or you don't need to close on the specialization, depending whether you take thick subcategories or what I'm going to talk tomorrow, localizing subcategories. Right? To the corresponding the G for any G, and even for the category with a corresponding notion of right. So I wanted to describe these two examples because in principle they look very different in nature. So you are looking at a stable homotopy theory and Moravacay theories. Then you have module representations. They look very different, but at some point there is some common framework in which they match. And then there are some techniques, there are something running in the background which makes that these two classification theorems are possible. Right? So what I'm planning to do in next talk is to describe which is this common framework in which these two examples fit, and then what can you do when you have this machinery running in this higher level. Yeah? Okay, so thank you very much.